Let's talk about implicit differentiation. So say that we have something like xy is equal to 3. Now notice how this is a function where it's not just like y is equal to and some function of x, like something like y is equal to x squared, for example, right? We're given a function where the x and the y's, they're all on one side, they're all combined together, and sometimes it may be really hard or just outright impossible to separate the x's and the y's, which is why implicit differentiation is useful. Now, if y'all done implicit differentiation before, y'all know that you got to treat y as some sort of function of x. So if I'm differentiating both sides with respect to x, differentiate this, the derivative of a constant is just 0. And the derivative of this, you would have to use the product rule in this case. This is going to be the derivative of the left multiplied by the derivative of the right, which is just dy dx, right? That's the derivative of y with respect to x, plus, and then the right multiplied by the derivative of the left, which is just 1. So that's just going to be y. Right? I'm pretty sure it's like left d right, left derivative of right, plus right derivative of left. Left d right, right d left. All right, so here's our result. And to isolate dy dx, what you would do is pop this y to the other side and just divide by x. So dy over dx is just going to be equal to negative y over x. However, in some YouTube videos, you might actually see this done in a different way. You could say, okay, if I'm differentiating this with respect to x, right? I can write this in a pretty weird way, and it would somehow work out. Let me show you what I mean. So, sorry, this is equal to 3, but if we differentiate this is just going to be a constant, and then so this derivative right over here is going to be the derivative, left multiplied by the derivative here. So the derivative of y. Here, what I'm going to do is something different. So what we do is when we're differentiating y, whenever you take the derivative of y, you differentiate it like you're differentiating with respect to y. So in this case, the derivative of y with respect to y is just 1. So pretend, it's like that. But then you multiply it by a dy. And likewise, right, it's going to be right, the y right over here, multiplied by the derivative of the left. And we're differentiating this x right over here. The derivative of x with respect to x is just 1. But then we added a little dx here, which is pretty weird, okay? I know these steps might seem random if you haven't seen this trick before. And this is going to be equal to 0. But let's solve for dy dx, right? I move this to the other side, so I get x dy is equal to negative y dx. If I divide dx on both sides, and then I divide both sides by x, would you look at that? We have the exact same answer, right? Now, why does this work? Well, this is actually something known as the total differential. All right, so the total differential. And essentially, the total differential, right, tells us how it's basically just a differential, but for multivariable functions. All right. So if you look back at our original function, which is x times y is equal to 3, notice how that's just a specific case of a multivariable function. So if I have a function that takes in 2 inputs and gives out an output, notice how this x times y, that's considered to be a multivariable function, right? You would agree that's so. However, it's just that this multivariable function right here has a constant output. So you're saying that given an x value and a y value, you want it to have a constant output when they're multiplied together. And let me show you what that means graphically. So we have f of x comma y is equal to xy, right? That's our function. When we set this to be equal to 3, we're basically looking at the set of all points where our function height, which in this case is the z value or the output of our function, right? We're looking at all the points where this x times y gives out a output value of 3, right? So it would be these intersection points right over here. Okay? It would be like taking a slice out of our function, right? We set our function to be a constant height. We essentially take a slice out of our function with this plane. All right? And you might recall the regular differential from calculus, right, which is dy is equal to dy dx multiplied by dx. Is that if I have a single variable function, something like this, right? If I zoom in on this function, for a tiny change in x, which I'll call it dx, I'm just enlarging it to make this more clear, right? For a tiny change in x, what I can do is I can calculate the slope, which is dy dx. And if I multiply the slope by my change in x, right, you remember the formula y is equal to mx, right, plus b. But since we're talking about the slope, we're only focusing on this mx part. And so if I multiply my slope by my little change in x, I get a little change in my output value. So I get a little dy as a result of that, which is exactly what this equation is saying. Now, if I take a look at the total differential, well, that's basically saying, well, how does our function change in the output, right? How does z change, right? So you can think about f of x comma y, that's the same thing as z, or just our output, right? How does z change with respect to both x and y? Well, we can write out the differential in the x direction. I know that a tiny change in z can be caused by a tiny change in x multiplied by the slope in the x direction. And in addition, because this is a multivariable function, the change in the height of our function, right? Think about it. You're on a hill. You can walk in both the x direction and the y direction. And in either case, you're going to be affecting the height in some way. So I can write out essentially the differentials for both the x direction and the y direction. Okay? So let me show you what I mean. So like if I was on this point, for example, a tiny change in the x direction would cause a change in height multiplied, right? So dx multiplied by the slope in the x direction, essentially. And then if I move in the y direction a little bit, that's also going to cause a change in height, right? When I multiply dy by the slope in the y direction, dz dy. However, recall that our function is at a constant height. So if I'm on a hill, but I'm on a constant height, my function, my output, is not changing at all, right? My altitude is not changing at all. So in fact, for my total differential, for this specific case, dz would be equal to 0. So we're staying on that same flat terrain. And let me just copy and paste this. So there we go. This is getting to the good part, because guess what? We can apply this formula to this right over here. Let's do this. All right. So if I take the derivative of x and y, and in fact, when you're dealing with multivariable functions, these are actually partial derivatives. Partial derivative. You want to tell the person doing this problem, hey, this is multivariable function. Our z is both influenced by a tiny change in x and a tiny change in y. So let's do this. What's the derivative of this with respect to x, right? What's dz dx? Partial z, partial x. Well, when you're doing a partial derivative, remember, you keep the other variable constant and you differentiate normally. So you treat y as a constant and just differentiate x. This is going to be equal to just y multiplied by dx, right? You treat y as some sort of constant. And the reason why you do that is because you're only looking at the slope in the x direction. So if I move my x value by a little bit, my output value is going to change. But you know what's not changing? My y value. I'm keeping that constant. I'm only isolating that change in x. So that stays constant. Same thing here, right? What's dz dy? Well, you differentiate this y right over here with respect to, you differentiate this with respect to y. But this time, right, you keep the x constant. So this is just going to be equal to x, right? The partial derivative of z with respect to y is going to be equal to just x, right? If you treat x as a constant and y as the variable, and multiplied by dy at this end. And recall that this is all equal to 0. And guess what? This is the exact same scenario we had right over here. And so you're able to say, okay, I want to solve for dy dx, and then you solve for dy dx, and then you get the same answer here. But I just wanted to show you this because that trick that you might have seen on YouTube, that just stems from multivariable calculus. Have a great day.